You have to register a Kaggle account and agree to the terms of the competition and their terms of service and stuff like that. And also, if you want to try to follow along, you're going to probably need your laptop probably needs to have at least 8 gigabytes of RAM, I would say. We're going to do a lot of processing during this during the script. For those that don't know much about Kaggle or know anything about Kaggle, it's a platform that hosts predictive modeling competitions. Those competitions are sponsored by companies like Facebook, BNP Paribas, which was the company we're going to use, Expedia and State Farm, and many others. A lot of competitions have prizes that range from $500, and I saw one that was 2 or 3 years ago that was up to $500,000 in prizes. And there's also, they have recruitment competitions, so if you're looking for a job, they have competitions, and like the top X number of people get interviews and stuff like that. The main goal during this workshop is that we're going to focus mostly on feature engineering type stuff. We might cover a little bit of ensembling, but the main focus in Kaggle is to basically make really good features and make a really good single model, because your ensemble is only going to be as good as your best single model. Well, it's going to be better than that, but it can only be, yeah. So the competition that we're going to go through is the BNP Paribas competition that ended in April, I think. Just about the data set, we were predicting a binary outcome. We were trying to predict whether a claim was suitable for accelerated approval or not, and the metric was a log loss. The training observation, or there was 114,000 training observations and 114,000 test observations, so it was pretty much split evenly. And there was 132 features total. 19 were categorical and 114 were continuous. One of the reasons we chose this data set was because it can fit on your laptop easily. You don't need like an AWS instance or anything to fit all the data on there like you do for some competitions. And also I was able to get, without ensembling at all, just using just feature engineering, a top 10 result. Actually in this competition, me and my team, we finished 4th after ensembling and stuff. But just doing feature engineering stuff, you can get a top 10 result. All right, so I'm going to start going through some of the code now. First thing we do, obviously, is just load some of our packages that we're going to be using. Data table is probably the most frequently used one in here. It's important to have that one. It's also really fast. If you are following along or trying to follow along, you're going to want to change your working directory to wherever you cloned the GitHub repo. And also, if you don't have that much RAM, you might want to reduce the row sampling a bit. Right now, this whole script on my MacBook Pro takes about 20 minutes to run if I just ran it straight through. So if you think it might take longer on your laptop, then you can just reduce the row sampling a bit. Yeah. Second thing we do is we're going to import, there's a script on the repo. It's just a utility script. It has a bunch of functions that I commonly use in competitions. You can use them too now. We'll go over the functions in a bit. These next few things are, this is basically a list of feature interactions that I got from my teammates. Dmitry, not Dmitry that works with me, but different Dmitry. And he got all these from an XGBoost model dump, and we're going to go over that in a bit. Basically, it shows what features interacted the most in an XGB tree. But we're just going to import these first. Should be 3 or 4 of them. Yep. What was that? I'm going to explain that in a second. So we're just going to import the train and test set, the entire thing. That should take a second. This part here is just doing the row sampling. Most of it's just, if you change the row sampling numbers, then it's going to choose different samples for you. That's all it's doing. This next part is just picking the CV folds. One of the important things during competition that you have to do is decide how you're going to do your validations and cross-validation. You want to choose that based on how the train and test data set are split. So if you are working with like a time series, for example, and the data set is split, if it's over a year, and the training set is like January through August, and your test set is the rest of the year, then you want to kind of split your data set in the same manner. So you'd maybe have the first 6 months of the year, January through June, be your training set, and then July and August be your validation set. So you want to kind of keep the splits the same. This competition, the split was just 50-50, and it was split randomly. And so in this case, we can just do cross-fold validation. We don't have to worry about splitting it in any particular manner. Just do 5 random folds, basically. And also, I usually choose my folds based on the size of the data in the competition. If it's a small data set, then I'll usually do more folds. If it's large, then I'll do fewer folds. The reason for that is early in the competition, or just maybe the first month or so, you want to iterate really quickly. And if you are doing a lot of folds, if you do like 20 folds, then you're going to be spending a lot of time training models. And you, in my experience at least, don't get that much improvement comparing your 20-fold CV compared to like 5-fold CV in terms of your scores and stuff like that. So usually 5 or 10 is good enough. Yeah, it usually gets the job done. So let's see, what's this next part? All right, this next part, I'm just binding my train and test set together. One thing I do is, you can see, oops, why can't I click it? Anyway, right here. I had a little filter so that it's just a column, all the zeros are in the test, or all the zeros are in the train set, all the 2s are in the test set. That way I can just keep them separated. That's going to be important later. Also, another thing I add is the average response. The reason for that is, we'll see later, I have to use it to calculate some things, so I like to keep it in the data set. Yep.
Can you enlarge the font a little bit so that our audience in the back can see?
I don't know. I mean, I could just zoom.
Yeah.
It's like it's in almost too close, though. All right, so basically the first thing, or maybe the second thing I do after I get the data loaded is, well, the first thing I usually do is check how many numeric columns there are, how many categorical columns I have, because that will kind of usually dictate the kind of pre-processing I have to do for certain models. And then the second thing I'll do is usually build just a baseline GBM model. GBM is really good, it's really fast. And the reason for building the baseline GBM is because we're going to start adding a ton of different features, and we want to make sure that after we add each feature, that we can build, we train a new model and it improves our score. We're not going to train a model every time we add a feature here. That would take way too long. So I'm just going to add all the features after we do this, add all the features, and then we'll compare our baseline to our final model. So one thing I'm doing here is, well, I'm using XGBoost. XGBoost only takes in numerics in its data matrix, so you can't just feed in straight categoricals like you can with H2O. H2O, if you have your categorical columns, you can just feed it straight in. XGBoost needs things to be in numeric. So one thing I'm doing, you can see here in this for loop, is I'm setting all the data table reads it as a character column, so I'm changing to a factor, then converting the factor to numeric. Even though it's a categorical column, encoding it as a numeric still works really well half the time, without doing any dummy encoding or mean encoding of it. So usually I'll just convert things to numerics and run it through XGBoost. Another thing I did right here is convert all the NAs to -1. If you looked at the data set, you could see that all the numeric values are all between 0 and I think infinity or something like that. There's a few different ways you can code NAs. Obviously, you could impute them, or you could use the median value of the column, or another way is to just encode it as a number that's outside of the range, because then XGBoost or another GBN will just split on the tree. It'll send all the -1s to one side and all the other values to the other side. That's usually pretty good at picking up on that. And my decision to use -1 here was just that it worked the best when I was trying things. I also tried using the median of the column or the mean of the column. And XGBoost can also accept a missing thing for NA, so it's like missing NA, and it can split on NAs too. But I found that encoding it as -1 worked the best in this case. So let's just, play. All right, so this is XGBoost is running right now. It doesn't take that long. I think it takes about a minute. Another good thing about doing your baseline model is tuning. Since you haven't done much to the data set yet, I usually do a lot of tuning at this stage. Usually you can narrow down kind of the area, and you can do it pretty fast. Sometimes I'll do grid search for tuning. Other times I'll just tune it by hand. Basically, what I do for tuning, usually I'll put like the learning rate or at 0.1. I'll keep subsampling and call sampling by tree, usually about 0.7 or 0.8, and then I will just move the max depth. I'll try like 3, 5, and 7, 13 until I find something that works good. And then I will usually start changing the subsampling and call sampling. Usually I find that a subsample of about 0.8 and a column sample of 0.4 or 0.3 usually works really well. But I usually find myself using for subsampling and call sampling either 0.3, 0.7, or 1, and 0.3, 0.7, or 1. Then last, I'll usually tune min-child weight. Usually 1's always the best, but sometimes usually 5 or 10 works out pretty well. All right, so XGBoost is finished running. We can see that our best CB result was about 0.4892. So that's our baseline. So that's where we're going to go from. That's what we're going to try to prove upon. Okay. See, the problem with zooming in is I can't see the play button.
Branden, do you want to take some questions for it to be more interactive?
Sure. Does anyone have questions at all?
If you have any questions, please just...
Yeah, just raise your hand during it, and I will see you. It's fine.
If not, just feel free to go on. It's a workshop, right? So we want everybody to participate, but at the same time, you know, we really respect what they want to ask. So
Okay, so what I did here was I just trained another XGBoost model, but I didn't do cross-validation on this one. I just trained it on the entire training set. And XGBoost and also H2O has a function that will give you feature importance, which is really cool. So we can see that obviously feature 50 up here is important, feature 12 is important, 114 is pretty important, and so on. It goes down from there. Another really cool thing that another Kaggler actually made this tool. It's on GitHub. It's called XGB-Phi. And what XGB-Phi does, instead of showing just the importance of a single variable, it basically shows down each tree like how often certain variables get split together. So like maybe a split on 50 happens on the top here, then a split on 12 happens down here, and then a split maybe could be back on 50 again on the third leaf or branch. So what we've done here, we basically dumped the XGBoost model, and then you have to do a separate process to run it through XGB-Phi. You have to do that in command line. I'm not going to show that, but the instructions on the GitHub for the XGB-Phi are pretty simple. But I can show you the output. Yeah.
Can you go a little higher and explain the steps which you went through? I mean, looking at code is okay, but I mean, how many iterations did you do to?
Yeah. So so iterations for getting to this point.
I mean, how the iterations you went through to get the parameters, which ones are right? You go out of the Jupyter notebook and do something, right, and then come back. Is that the process you are doing?
I don't usually work in Jupyter Notebook. I usually work in like RStudio.
Because you said something about installing the XGBFI or whatever.
Yeah, XGB-Phi.
Right? Yeah. So.
Yeah. So to install that, you have to clone it off their GitHub, basically.
And that's not iterative. It's just that he trained a model,
yeah.
and then he used a function on here to analyze it.
Reading the code which is on the screen, I'm trying to understand the steps which you went through to get to this point, right?
So you want to know what this does, basically?
No, at a higher level,
Yeah.
the process or the steps which you took, right? You do all this, right? At some point, you have to do that XGBFI or something. Right?
Yeah, I'm doing XGB-Phi right here.
Right.
In this part.
It doesn't seem like it's as straightforward as what he's got, and especially because those variables are loaded up front. But actually, this part does run fast. He's talking about loading a data frame. He hasn't really made any decisions at this point other than enforcing the right data types, run a model, and he said that was a fully fit model, right, because this is one of the first things he's looking at is the feature interactions, actually. Right. So there's not any modeling decisions. This is where the modeling decisions start, to just look over that data frame and start to think about what that's telling you. Okay. So it is one of the intro steps, if I'm reading that. I think that's what you're saying, Branden, right?
Yeah, this is like one of the first things I do.
Yeah, so he's got an XGBoost model, kind of played around with the parameters really quickly for a baseline model. And that's it. There isn't a whole lot of thought so far. This is where it starts, is when you start interrogating your models. So the data types are a force thing. Like he says, H2O is not going to force you to do that. And we want to get some of these feature interactions in H2O as well. But I would follow the same process. Load the data in there, maybe start a model. Sometimes, kind of like he says, I'll look at it a little bit, try to understand what the data is about. But I do generally run a model pretty quickly to just see, is this easy to predict? If I see an AUC of like 5.3 or something like that, I know, whoa, this is going to be hard. If I see one way up at 9.7, it kind of sets you for what you're about to see as far as how easy the problem is to predict. But then you get to also start looking at the variables and start thinking. These, unfortunately, a lot of the Kaggle competitions, they are anonymized, so you can't even really read the variables. But in your real data sets, those are very, it's interesting to read through the feature list and think about what's the best. And the feature interactions is telling you what things pair together. So even though it feels like there's a lot of code you've looked at, once you get in the habit of running a lot of these lines, this part's actually pretty fast to go through this. So I don't think there's a lot of stuff you haven't seen, as weird as that does seem.
I guess I understand what he was saying. instead of looking at the code line by line, we could just say the first step we do this, and then kind of like explain how do we do the feature, find the best feature, the general high-level approach before we dip into the code. It's easier to follow than the.
Because so far that hasn't been done. Like
I guess, yeah.
The model call itself, like this just is printed out. Like H2O, any model you have, I don't have to ask or think about it. I'm just going to see my feature importance list ranked. It's very insightful. And then the feature interaction is kind of the same way. So there's no thought, but that's where maybe it starts. Maybe it can expand from here. But I don't think either of us at this point would have done any of that so far. So load the data, run a baseline model, and now start interrogating that model. You get a score, and you're going to use that score continually to check how your models are improving. He'd actually also said that the cross-validation technique, so you want to be clear on what that is, thinking of how this generalizes to your future data. In Kaggle, you can observe how the train test split is. Maybe up front you don't worry about that, it's up to you, but in the real world, you definitely have to pay a lot of attention to that. But at that point, that's really where we're at. Run a model, and I think, there's a lot of parameters on there, and it might seem like those are tuned parameters, but most of us go with some pretty stock parameters just to start that are fairly stable. So I don't think any of that's been done, but maybe like from here and how you interpret that list or something like that, or how you would interpret that list maybe. Sorry, I know we're not really getting at what you're asking, but I think.
What's the environment like? You're doing this on your laptop, so you have a cluster available. Are you doing this all in R with R packages, or are you going to be using H2O? What's the environment like?
For this competition, this is before I was even working at H2O, so I didn't hardly knew what H2O was at this time. This was like 6 or 7 months ago. So what I usually use, is RStudio and R for the most part. For as far as clustering and stuff like that, our clusters go. I have a desktop at home that has 128 gigabytes of RAM, so I do a lot of stuff on my desktop. I will also do a lot of stuff on AWS or on our servers at H2O sometimes now.
And for me, I typically, same kind of thing, RStudio inside my MacBook Pro, which has got 16 gigs of RAM. And for easily 90% of Kaggle datasets, that's actually all you really need. So I'll typically do modeling, a lot of data table stuff. I say modeling, actually, looking at the data. I also am a big fan of data tables, so I'll do a lot of that, kind of look around, do some things, spin up H2O, push the data into it, run a GBM with the same parameters almost every time. And that's where the thinking kind of starts. Then I'm going to go back and maybe go a little back and forth between what I've got saved in data table versus what's saved on the cluster. In the times when I really need a server bigger than 16 gigs of RAM, which again is very rare for the Kaggle competitions, but and especially customer data sets, things like that are legitimately large, I'll still sometimes, I just like the fluidity of working on my laptop sometimes and portability. So sometimes I'll subset some of that out, but sometimes working directly on the server, because that's what's cool too. So we can use H2O servers and still remotely control everything that way by just connecting to the server. So you're still kind of, it feels like you're working locally, even if you're not. That doesn't apply to the data table type calculations, but things like that. So yeah, it's very quick. I guess a lot of times, a lot of people, especially teammates I've worked with, think of the feature pre-processing separately, and they'll modularize their code sometimes to where all that's done. And you can do that in H2O. We do have munging in there, but we have some work to do to catch up to what's possible in data table and pandas still. So a lot of us locally will do the feature engineering, but maybe not too much of it. I think the biggest thing, that iterative thing that he said is, especially like I said, the front half or third of the competition, you want to iterate really quickly. So you don't want to think through all, like 100 features that you might want and all this complex stuff. You really want to get that baseline model and use it like a baseline model and test your features quickly. So I think getting a model up quickly is a useful thing. So hope that helps. Yeah. Pretty small, like 100,000 rows.
It's 230,000 rows and 130 columns or so. So I think it's like less than 100 megabytes or something like that, just in its rawest form, or maybe 200. But one thing I want to say with regards to the RAM size, he was saying he runs it on his laptop and stuff. For this particular one, for this particular problem, running this script, if you ran it for the entire length of the data set, the entire training set and test set, it like maxed out my 128 gigabyte RAM computer at home. Because I was doing a lot of parallelization, so that took up a lot of space. And if you don't do the parallelization, it takes about 24 hours to do all the pre-processing that I need to do. So by parallelizing it, I maxed out my RAM, but it runs in 3 hours or so on the full data set. Yeah.
Hey, you guys seem to be, competing in Kaggle for a long time, and you guys seem to be really a pro on that. What I have to tell is we are kind of new to this. I'm pretty sure at some point of time, even you were new to this, right? What was your, your steps to understand about feature engineering, right? So let's say a data set is queued, a data set has a lot of NAs, or a data set is basically cleaning the data set, right? So you also started somewhere long time back. So what was your step to understand all this thing? I mean,
the biggest step to understanding all this is reading the forums, for sure.
Reading the forums.
The Kaggle forums are like some of the best. People love sharing information on there.
Yeah.
And they love sharing information about active competitions. Some of the things that we'll see soon, like I wouldn't have figured it out on my own, but someone had posted it in the forum, and it ended up working like really well in the model. And then once you understand that for this competition, you recognize it again for the next competition. You're like, oh, I could try this here and look at it this way here.
Yeah, I would agree. I mean, I come from kind of an ETL warehousing business intelligence background, and so the first Kaggle competition I had pretty decent luck at, and it was kind of like an affirmation that I kind of guessed at how some of this works. So I had a decent idea of how the machine learning models worked. But yeah, to see, once you figure this out, it actually is common to what people in business intelligence do. You have to roll your own calculations all over the place, and that's a little bit of what we're going to see here. Like machine learning, people think, shove the data, hit the tool blender, and go, and that won't win a Kaggle competition. It just won't. So we want to automate as much of that as possible in what we're doing, but yet the people that are at the top, are consistently there with techniques, and I think it is a lot of learning how to do this and then recognizing when it's appropriate. Otherwise, you would be able to treat it like a feature factory and do it all the time, but there's just something a little different of how we see some of these things, like this conditional logic. But so I think doing the competitions, to me, I always kind of describe it as like this kind of large-scale homework assignment, where the whole idea of homework in school is to do it and then realize where you're wrong and then fix it. So that's kind of what happens. Every time the Kaggle competition happens, you struggle with this data set for months on end. And at the end, within almost 24 hours, you're going to read a lot of people that did better than you, and you're going to read these things that they tried. And so there's never a better time to absorb that information, because so it's easy to read a book and wonder and see, okay, oh, that sounds like a great idea, and never know when to apply it. It's hard to stick. But you know that you didn't see this coming, and that person didn't. It looks so simple a lot of times when they do it. So you just kind of have to figure out how to match the techniques that you didn't see so that you can do it next time. And I think that's what a lot of us have managed to do by how open Kaggle is. It's amazing how it's almost been a long time since they required solutions to be posted, and yet everyone's really forthcoming, which kind of works disadvantageously for their future standing. But that's amazing that that's the case. So keeping up with it, but I think really taking a data set that so I like that part of struggling with it. I think that's important to me, at least, and how I learned how to apply what I see.
Hello. My question goes regarding feature interactions. In this case, you used XGBFI.
Yep.
I guess you can also use factorization machines in FM or FFM, whatever it is. But my question goes, and probably Arno can answer this, the neural network does that, correct? That interaction between features.
I want to say one thing first. Like the XGBFI is simply informative. It's not a model. All it does is look at the model you have sitting in memory and figure out, it's a transparency tool. It's not a model at all. So you could take that, so factorization machines will encode that differently, but the XGBFI hasn't done anything necessarily. So it would be more correct to say that factorization machines explicitly cover 2 and 3 and 4 and whatever, however many interactions you want to say explicitly, whereas a GBM handles it implicitly. People call it, interaction depth is the way that the one in R is called. Yeah, maybe, but technically yes, I guess, but it doesn't really work the same way. as a classical GLM or something like that, where you can encode your interactions by hand. So the FI part, which maybe seems to confuse some people, it really is just informative. So it's to look at what it's doing and tell you as a modeler what might be interesting so that you can prune the rest out. You can make it see these more clearly. There's still a way to do that. So it doesn't have to struggle with all the things, because you can I guess it helps probably to have this mental map of how a decision tree is working, but how an interaction, it's a really complicated thing, how the decision tree finds it, and it almost feels like it's a random chance whether it can find it. It's not random, and it does a good job at them, but it cannot find a lot of complex interactions. So you find, like, mathematical properties are a great example. Dates, like the second some of us see dates, we know to start taking differences between them. Technically, your interaction, you could put them all together and you find, or you can find it if you don't put it as an interaction, it has almost no chance of finding what's really there. The real relationship is there. Decision trees, it's very expensive. You're going to need tons of trees to do that, or tons of depth either way. So that's where the whole idea of feature engineering is to try to present the model some things that it's not good at finding itself. They're good at finding interactions, but if you go above and beyond and really force those in, that's where it does it. But yes, neural nets technically will find interactions, but go and calculate them, I guarantee you'll get a better model. Factorization machines are a whole different animal. I'm not sure what would happen if you put a ton of those, if you maybe one-hot a whole bunch of things in factorization machines. But yes, those are models that definitely are designed to take interactions, specifically factorization machines, and deep learning does technically, but I think in practice...
I saw that above, you have columns 50 with 64 and as a one-way, two-way, three-way, four-way. You're using the result of the XGBFI in order to do the feature engineering. And that's my point. And without it, the 47 with the 50 with the 50, XGBFI is telling you, okay, that combination did a huge gain. So you're using that as your feature engineering, correct? Or am I reading the code wrong?
Yeah, we're going to implement that into feature engineering.
Okay, so, but in neural networks, you don't have to do that, correct?
You don't technically have to do it here, because keep in mind, the GBM actually found these all by itself. Yeah. This whole technique is to essentially help you win a Kaggle competition instead of just doing really well. So it found these automatically, but what this is suggesting is that if you want to create the features yourself, you'll get a little more gain. And I would argue you definitely can with neural nets too, deep learning and as well, especially with these transactional type data types.
I think some of the confusion may be coming from the fact that you loaded the these features in beforehand, but for clarity, I don't believe those were used in your baseline model. Is that correct?
No, those were not used. I didn't do any feature engineering. I didn't use those at all. That was just loading before because I got those from my teammate during the competition. I'm just showing XGBFI here because that's how he ended up getting them. You'll notice here that none of these really match what he provided me, or I'm sure some of them do, but that's because we ran this on about 5,000 rows of the data set. He ran it on the entire data set and probably had different parameters than me. But yeah, so that's what we fed in at the beginning. So we output all those our XGBFI interactions. We'll come back to that in a bit. Right now I'm just re-importing my train test set, just redoing that part. One thing that someone had noticed on the forums, I didn't notice at first, was that columns 91 and 107 are exactly the same. So since they're the same, they're redundant, and we can just get rid of 107, or you can get rid of 91. And this one is another one that I also wouldn't have noticed if it wasn't for someone posting it on the forums. If you look at V10, and this is a good reason to build histograms of your numeric columns and stuff like that, and just look at them. If you look at the histogram of V10, you can notice that we have a bunch of spikes, and all the spikes are pretty much evenly spaced apart. So one thing that someone had conjectured was that it's actually a categorical variable that was converted to numeric and then maybe added some random noise around it. So one thing that ended up working was basically undoing all that. This number here is what was posted in the forums. basically, if you divide V10 by this number and then round it to 0, you end up with, I think, like 10 distinct groups, basically. And then eventually we're going to just convert that to categorical. So that's one good reason to read the forums. This real quick. This might take a bit. So one thing with this data set was there were a lot of missing values. Like a lot of the rows were missing like most of the values. You can actually look at this missing this map, and you'll see that all this white stuff here, basically, that's all missing values. So you can see that a lot of observations only had observed values over here. If you look even closer at this, it's a little hard to see. You can kind of see that there's almost like groups of missing values. So like it's almost like this group here you can kind of see. And then at the very end here, you can kind of see this little like kind of subgroup, where some are missing values just kind of here at the end. So one thing that we're going to do is we're going to basically cluster, use k-means clustering on the missing values. And one of the reasons for that is it just makes it easier for a tree model to find its splits. Because rather than having to split on a bunch of different columns in order to identify, oh, this fits this missingness kind of pattern, we can just identify the pattern using like k-means. In this case, we did 7 clusters. And then we just add the clusters as a factor into our data set. That was just kind of tuning. So I tried 5, and I ran it all the way through and trained a model on it real quick. And then I tried 7, I tried 9, and 7 ended up working the best. Another way I do it sometimes is look at how big the cluster sizes are. Because sometimes I'll do like 9 clusters, but one of the clusters will only have like 19 observations in it or something. So I try to just... What's that?
The chart or the arm.
Yeah, you could look at that too, yeah.
Okay.
But like I try to make it so that my clusters are, I don't want to say even, but so I have like a large enough sample within each cluster. Maybe like 500 observations or something like that.
And if you have questions, please wait for the mic to come to you, because we want to catch your voice on the audio as well.
Next, we just kind of do some like row summary type variables. For example, we'll just find the max value of an observation of its numeric values, the min value across it, what the mean of all its numeric values are, standard deviation, median, stuff like that. These little things help. Also do counts of NAs and counts of zeros. Sometimes those are those help out GBMs or neural nets a lot. Dun, dun, dun. What else? Another thing I do, so you don't really have to do this part. Another thing I do is anytime there's a blank value as a character or as a factor, I usually just change it to be null, or so it just writes out the word null or blank. Sometimes I get errors if I just leave it as double quotes. That's nothing major. Here I'm just converting my character columns to factors. And then I'm also converting these numeric values down here to categoricals as well. The reason for that is a lot of these have very few unique values. So it helps to sometimes make them a factor. If you're doing like, if you're going to dummy encode them, you can dummy encode them. Or do whatever you want, whatever other types of things you do to a factor column. Here I'm converting NA back to -1 again, because I redid the data set, or rebinded the data set again, so I have to redo it. And this next part here, this part is part of the caret package, C-A-R-E-T. All I'm doing is removing any columns that have 0 variance. It's just something I usually put in just to make sure I don't have anything without or with the 0 variance, because that doesn't help out your model very much. All right, so I'm going to run all these right now because they take a little bit of time to run. Or I can just do this. Actually, I'll run this too. Okay. 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 So I think I mentioned earlier that, or maybe didn't mention, there's one or two categorical columns that have what's called high cardinality, meaning that I think one of them had like over 4,000 distinct categories or something like that. So one way you could do that is to dummy encode them, which isn't always the best way because then you're just blowing up the size of your data set. And you can either run into memory problems or it doesn't work as well when trying to train models on it. Another common thing to do, as I mentioned earlier, was just encoding it as a numeric, which works sometimes, works kind of well, generally, but it's not the best way to do it. Usually the way I go about this is what's called mean encoding categorical variables. And there's a paper on this. I think it's in the notebook. Basically, the idea is if you have like a high cardinality categorical, or if you're trying to encode feature interactions between two categoricals, because that can also, if you do interaction between 2 or 3 different categoricals, then you're going to end up with a bunch of different unique combinations. So a good way to do that is to encode them as the mean of the response in your training set. So for example, you have feature 1 here, and there's 4 of category A, and the outcome for those is 1, 0, 1, 1. So the average is 0.75. So you could encode them like that, but you run the risk of overfitting. And for example, if we just had 1 C down here, and its only outcome was 1, and then we encoded it as a 1, then that would kind of be, it would be cheating, basically. You'd have the answer, and you'd end up overfitting your model. So one way to avoid that and to reduce bias is to do what's called leave one out encoding. So when encoding this first feature A up here, we're going to leave out that outcome 1, and we're going to encode it based on the average of the other 3 A's. So the average of the other 3 A's is going to be 0.66. So the first one, we're going to leave one out encode of 0.66. And the same goes over the second one. We're going to leave out that outcome. All the other A's are average of 1, so that gets encoded as a 1, and so on. So that's one way to help get rid of the bias. Although still, even if you do it this way, you still end up doing a lot of overfitting, generally. No, this is one of the functions that we imported earlier in the utils. It's actually, where is it?
Oh, you created a function against it.
Yeah, I created a function. It's in the utils file on my GitHub. It's not very big. So I see this function here, categorical, n-way, average. And the CV stands for cross-validation, but I'll explain that in a bit. So like I said, leave one out. It does better, but it's not the best way to do it. So rather than simply doing leave one out encoding, what we're actually going to do is calculate a weighted average between our leave one out number and the overall mean of the entire data set. And the weights of how we weight it towards the leave one out encoded one or the overall data set is going to be based on the frequency of that particular factor level, or how frequent that combination of feature interactions happens. So,
question.
Yep.
How do you handle the missing categorical value? Let's say there is a D in the test, but there is
missing categorical. I just encode. I just change it to be a new category level. So rather than being
if
missing,
it is not there in the train, but it comes in the test, how do you handle such situation?
Oh, in this situation, then it would get encoded as the mean of the overall data set for this. Is that what you're talking about?
No, I got the ABC, but I'm saying that let's say there is a D coming in the test one, but you don't have that value in your trained data set.
Yeah, so that particular combination or that particular level won't be in the test set. So what's going to happen is that anything that doesn't show up in the test set, or doesn't show up in the trained set, but it's in the test set, will get encoded as the overall mean for the entire data set.
Okay.
So, for example, for the outcome, the overall mean for this is 0.77. So if a D came up and I had to encode a D, then I'd end up encoding it as a 0.77 eventually. Yep.
So in this case, you've got a binary response, right? You've got 0, 1 that you're predicting. If you've got a multi-class problem,
yeah, so
how do you encode?
I've actually tried this on multi-class problems, and I've struggled to succeed with it so far, although one of them was on the Expedia competition, which was a very big data set, so it was very slow to do training and try to figure out if it was working or not. One way I was trying to do it was actually, rather than encoding each one as just the binary outcome, I'd have basically 13 for each category, what the probability is for each category.
Okay.
Yeah, and that's tough to see that scaling. I've been in the case where, okay, I like this method as well. And yeah, there was one with about a dozen. So we created a dozen fields for everything we wanted to use this technique on. So it feels uncomfortable. You're all of a sudden generating, to me, 200, 300 type variables. It starts to get large. Brandon's way beyond that. But that actually worked really well. And especially and sometimes I'll actually, in that case, yeah, if you have a multinomial problem and you have, a manageable size, you can automate that in the code to get those columns, and it actually does pretty well. But there's probably a practical limit. I haven't done anything with like 1,000 or something like that.
So as I was saying, rather than just using the leave one out encode, we're going to do a weighted average between the overall mean of the data set and leave one out encoding mean. Basically, the function to do this looks something like this, whereas on the x-axis is the frequency of the categorical. So in our example that we had before, there was 4 A's. So we'd look down here over at the 4, and we'd basically go up. If we're using this blue function or the red function, I'll explain that. But if we're using the blue function and we're looking at A and it had 4, then we weight A at almost 90%. So if we go back over here, which is what I ended up doing, so this is the weighted encode column for A. You'll see that it's very close to its leave one out encode because 90% of the weight was put on the leave one out encode. Whereas if we look over at C, which had only 2 observations, the weighted encode is, it gets almost halfway between 77 and 1, which I think if you look back at this, actually I think the inflection point on this blue line is it's at 50%. I set it to be that. And this function here usually has to be tuned sometimes. I usually find that using k equals 10 and k equals 20 and f equals 10 usually is about where I start, and usually that works pretty well. But you do have to do a little bit of tuning for that. And it's also based on, just have to do some tuning for that. Just here, as I said, k controls the inflection point. So on this blue line, k was 2, and f was 1 on this blue line. On the red line, the inflection point was at 20, and I think steepness for f was at 10. Yep.
So this seems like a really cool trick for dealing with categorical variables in Kaggle competitions. Do you also find that this works for business use cases too? Like,
at my last job, I was actually, I encode it like this.
Okay.
And another cool use of this too is, it's mentioned in the paper, is doing like encoding zip codes, because zip codes are hierarchical. So if you have a zip code that's like 9510000, then you can use the mean of the 9500 thing. Instead of going for the overall mean, just go one level up and use the mean of that.
So I saw a really cool presentation last year on GLRM where they were showing how you could use zip codes and do like PCA to sort of, instead of having all the different categories of zip code encoded into like the first principal component or something.
Cool.
Have you compared this method to something like that GLR?
No, I actually haven't. But
Just
that's
curious.
a good thought. All right, so basically what I just explained is being basically applied here to three-way interactions. So basically what I did here was I have all these columns that I want to use for my three-way interactions, and I just find every possible combination of them. And I basically encode each combination of them as the method I just explained, the mean encoding. And I also am doing counts of them too. So I'm doing counts of how many times a certain feature interaction shows up. So here's kind of where, at the very beginning when I loaded in all those interaction features that I got from my teammate, that's kind of where I'm feeding this into here, into five-way interactions. And I'm using all the interactions he had, and I'm just interacting it with V22 here. V22 was the highest cardinality categorical. It had 4,000 different levels, and people found, and I found too, that it was really helpful and as far as predicting this case. And I also went even so far as to do seven-way interactions, which is not a very common thing to do, but I just kept going up until I stopped getting better models. I actually tried 9 and it got worse, so I stopped at 7. Usually just doing 2 or 3 is as far as I'll go, but this one worked, so I stuck with it. Beyond 3, I tried 4 and it worked, and then I tried 5 and it worked.
Yeah, I mean, people, as you said, don't go beyond 3-way, right? So I'm really curious to know, like.
I mean, people will go beyond 3 ways. Like, there's no reason to just try things and see if it works. That's why it's good to be really iterative and do it really quickly, so you can just keep trying these things. Like, that's why I parallelized it and did it on my my desktop at home, was because I could do this. I'd have to redo this every time. It would take 3 hours or whatever to recalculate everything on the entire data set. So yeah, I just keep trying until I don't get an improvement, basically.
We have a question.
Yep.
So there's so much iteration along the way here. I wonder if you've systematized this to some extent where you keep it organized instead of just saying, I tried a bunch of stuff and then I remember that 7 is the right parameter or the right stopping point. Do you kind of keep a database of what you've done somewhere? I've seen some people doing
Some people
things
do
like that.
Some people do that. I'm very bad at doing that. And I'm lucky enough to have good enough memory of kind of what I've done before. Or sometimes, like, if I try something, I will just comment out the code if it doesn't work. That way I know I've tried it before and it didn't work before. And that way, and also if I want to bring it back again, I still have the code there. I can retry it if I've added something else that I think it might help it out later. So my method is not very good.
I'll keep up with it a lot in comments of what I've tried, because it's often good to revisit that list. There's a lot of times when you eventually stumble on something that changes the whole idea, or your perception of everything before it. So if at some point you're on a regression technique and you realize, whoops, logging the target is a good idea, you can kind of replay all the ideas, and some of those might change, like this thing that you discarded, because like Branden, I mean, to stay iterative kind of means you're trying as modular a change in your overall system as you can, and seeing if it's better, and believing in your validation results to tell you whether to accept or reject whatever you just did. So yeah, having that history, sometimes it's not often, but sometimes a fundamental change downstream can cause you to want to revisit some of those prior assumptions that you kind of made because you let validation tell you the answer. But I don't keep up with it, which was fun. When I'll work on teams, like there was a time where we would all meet up every week and we would kind of go over all the results. which kind of enforced a better framework on that. And so I was kind of drawing charts like this is what the ideas were. You know, you guys think that this method was working, but it didn't work any better. And everyone could kind of see. I usually keep up with the numbers too, so I can see kind of the magnitude of it, and you slowly start to absorb or stare at whatever your standard deviation really is too, because a lot of times after getting really deep in these things, the movement is almost random. But GitHub, I mean, that's definitely one of the things we're aiming for with like the model repository on Steam. That's people asking us a lot of questions about what we want to do to see this lineage of models, all these kind of things, because that's really what it is. If you're doing this in an enterprise scale, especially with an actual decision loop like in the morning, having that history in a better way than 2 dashes before the number is probably more systematic. But doing Kaggle competition, that's about as good as it gets usually for me. I mean, GitHub repos are good as well, but I've not gone to the extent of like saving things. If I know I'm going to do something, or I'm going to run a bunch of these in a row, like maybe I'll drag out a spreadsheet or something like that and keep up with observing, because I'm trying to figure out what's the structure here, what's the most important thing that changes. But most of the time, just kind of running through it and taking the best and assuming that's almost like a commit to master. Like that's almost my baseline model. Now let me try to improve that. Sometimes combinations of features, there is the interaction effect that maybe I've discarded some bad things, but that's pretty much how I work usually, is just keep moving on with that best model I have.
Okay. So like I said, we encoded all these feature interactions up here. All told, I think it was something like 7,000 new columns were created. That's why it takes like 3 hours to run, usually. So this next part here is something I got from a teammate, an idea I got from a teammate in another competition. The idea here is to calculate the correlation matrix for all your numeric features and find the ones that are the most highly correlated. And basically, if you find 2 columns that are highly correlated, we'll basically take the difference of the 2. And what that does is basically it almost produces a vector. Basically, have a lot of zeros, and it'll tell you where those 2 were like where they were different at. So if they're highly correlated, like you'll have a bunch of zeros and maybe like a large number where they're the most different or whatever. And that basically, it creates like an indicator column of when they're different. And then after that, we'll end up, then after that, we end up dropping, I think I ended up dropping both of those columns that I used just out of the data set, since I got the difference between the 2 of them. It's usually good enough. And since they're highly correlated, you usually don't want highly correlated features in your models because they're just pretty much redundant.
Unless they're negatively correlated.
Yes, sorry. Yes, you're correct. Correct. I only do it for positive correlations. Okay, next part. This is, I don't know if there's like an actual method for this. I kind of just made it up one day. Basically, the idea is, I made it up on doing a multi-class competition. Let's see, actually, the whole thing here. So the idea is that I identify columns for each class that help differentiate the class from other classes. So numeric columns can be used. And I only use this on numeric columns, and you'll see why. And all the numeric columns have to be centered and scaled before I choose the features. So basically what I do is I will calculate the z-scores for each feature and class combination. So for example, feature 1, or these are actually the means, sorry. Or no, these are z-scores. So basically what I'm looking for is to find features where the z-score for that particular class was the most different from like the rest of the data set. So for example, feature 1, most of them are pretty close to 0, so nothing's really differentiable. For feature 2, we see that for class A, the mean for it is negative, or pretty negative, negative 3.25. Class D is 4.23. And basically what I do is I find the features that have the largest values. And so for class A, it's going to be feature 2 and feature 4. For class B, it's going to be feature 3 and feature 4. And what I will do is I will end up adding those 2 columns together. And what that does is basically end up with a new feature column that is the helper column here, basically. So you can see here, helper A is going to be feature 2 plus feature 4, which are both zeros. And then, yeah, feature B is going to be feature 3 and feature 4, which ends up with -3, -2, and so on. It somehow worked on this binary problem. I usually don't do it on binary problems, but I tried it, and it worked. It's part of being iterative. But I think it usually probably works better when there's between 5 and 50 classes. And you need to have a large number of features. I think if you have too many classes, you're just going to increase your dimensionality too much. So I know there was one competition that had like a few thousand classes, and if you try to do a helper column for each class, it'd be, I mean, I know I have 7,000 columns here, but blowing up your dimensionality sometimes doesn't help that much.
So Branden, I know that you have a lot of tips for us.
Yep.
We are running out of time. Do you have any
That was the
words of wisdom for us?
Hold on a second. That was like one of the last feature things, so I think we can just.
And I would almost summarize. So a lot of this, and this may be confusing because we sort of went straight into the deep end. GBM is a really excellent algorithm for transactional data, which still is the majority of Kaggle competitions. You can usually spot text and image. You're going to want to work with our deep water type GPU frameworks. But GBM is an excellent algorithm. But it's one of these, like later when I do the top 10 data science ones, there's no free lunch. So GBM, I love it because I can think of my data and start creating things that I think are interesting, or pulling data out of a database or something like that. And GBM will worry about, it'll handle all the things that people have to hand roll when they use something like a linear model. So it doesn't have many assumptions. Like the decision tree is a really strong way to not care about your distributions, to not care about NAs, to not care about a lot of things that you have to think about when you use other models. So we kind of use that just to start because it is really powerful. But again, there's no free lunch, so that's good. But when you talk about like winning these Kaggle competitions, there's not much that separates Branden from the person in 50th place. And these techniques are kind of the above and beyond things that make the models go from good to great. Sometimes they're almost essential. You can get some meaningful separation, like with some of the, with sparse categoricals, your GBM at best is going to be inefficient if you don't do this. It's going to take you a ton of trees for the thing to overall fit the model. At worst, it just won't work compared to actually doing this. So there's definitely some validity of some of these techniques, I think, for every business problem. But if it sounds like there's a ton of work going on here, there is. It takes a lot to do one of these things. There's a lot of iteration. There's a lot of fairly fancy methods that don't give you a whole lot of gain, but it's kind of what's needed for these competitions. So the starting point usually is a lot of those things we saw up front, even the mean encoding. Those are things a lot of us will just roll out in the first few hours or days of a competition. And then you have more complex interrogation kind of methods too.
Last question. I wanted to find out what is the connection between what you just presented. This is Python, right? And Jupyter Notebook.
No, this is R. This is a R. Yeah, you can do R Jupyter Notebook.
Okay.
Yeah.
Because I thought it's the IPython notebook that you showed. It is. Oh,
but you can run R on it. Yeah.
Right. I know. Sorry. So the question is, I tried to use H2O for the all-state competition.
Okay.
But I'm trying to figure out, because I thought it's in the context of H2O that you would be doing this presentation. So I'm trying to connect the two.
I can say, yeah, most of these techniques will work either way. I mean, I use H2O for these competitions exclusively. I mean, sometimes I team up with somebody doing something else, but I did this competition, didn't finish anywhere close to where Branden did, but not bad. So these techniques, I think with our H2O GBM, are not unlike. There's very little that's explicit to XGBoost here, and we've tried to catch up. That's the power, that's the usefulness of having people that kind of are watching what's going on in Kaggle, is that when we see people start to use parameters, we've put them in ours as well. So a lot of our GBM looks way different than it did a year ago, and that's because we're watching what people are using in XGBoost. But like the feature interactions, we're not there yet. But everything else, I think, is going to be pretty standard here.
So that was the piece I was missing is, okay. Because I tried something and I got some result, but I didn't go through this step. So
Yeah, there's a lot extra here.
right.
So.
Okay. Thank you.
Okay. Well.